When we hear the word space, we usually think of something in 3 dimensions, right? An object in space, something like that. This is probably because we like to associate this word space with spaceship, space traveling, solar system, Earth, Sun, or black hole, something like that. We associate this word with the space that we live in, which is 3D. But it turns out that it's not necessary that a space has to be 3D. A space can be 1D, a space can be 2D, and it can also be more than 3, maybe 4D, 5D, multi-dimensional space. So let's take a look at what kind of a space it is when we only have 1 dimension to work with. So 1D space right here, 1D space is an empty region when we only have one value, one variable to work with. So I'm going to put an x-axis right here. Let's call this x-axis. And since we only have 1 dimension, 1 variable, we only have values for x. Put 0 right here, 1, 2, and keeps going. Alright. -1, -2, -1. And this is what a 1D space looks like. Now, what about 2D space? I think you know by now, right? You can guess by now that it's going to look like something that you used a lot in this subject, math. 2D space is an empty region when you have 2 variables, 2 dimensions to work with, and that is going to be 1 dimension right here, the x-axis, and then another dimension right here, y-axis. So it's the graph that we have seen lots and lots of time in several subjects. So we have 1, 2, 3, 4, whatever it is. I'm not going to name each one of this, label each one of this, but you know what this means, right? Right, it keeps going. So this is 2D space, and this is 1D space. So what about 3D space? The one that we live in, it's going to look like down here, 3D space. And once again, it's going to be an empty region when we have 3 variables to work with, right? I'm going to put a keyword right here. Space is about empty region. It's empty, it's just space. It depends on how many dimensions you have. All right, in terms of 3D space, you are going to have 1 more dimensions than 2D. Yeah, straightforward. So we have this first axis, first variable to work with, that is x, and then we have y variable to work with, second, and of course 3D, the third variable to work with, that is z right here. Okay, so you see something that looks like where we live in, right? 3D space. Now, we have these empty regions. Then, usually we want to put something, right? We don't want to leave it empty. We want to put something in the region. So let's put something in there. What about we put a point in the region? I'm going to put a point right here in the region. Maybe right here, empty region. And for this 3D space, I'm going to use the one that is already there, which is right here. Right? It's natural to put something in the empty space. Right? That is the first thing we do here. We have a point in space. Let's call it P. Every one of them, P. And I'm going to write it again, right here, P. Okay, now that we have a point in space, we don't want to just leave it there without knowing where it is, right? We have something in space, and the next thing we want to do is to find the location of this point in the space, right? So we have to find a way, a method to locate these points, right? And the way we do this, the method that we employ to locate these points in the space, to know where it is, is not just by pointing, but by using indices, by using numbers, all right? And we call this kind of sort of like having a location, pinpoint a location we call that coordinate system. I'm sorry. All right. We call that coordinate systems. So we are going to use coordinate system to locate these points so that we know where it is, not just there. So in this case, we are going to use this value of 2 to be the coordinate system of this point in 1D space. All right. So 2 is coordinate for this point. And then for this one, let's take a look here. I can use this y value of 2 and x value of 3. And with this, I can use the coordinate system for 2D space. And x value is 3. I'm going to put 3 right here. And y value is 2. There you go. Coordinate system is going to tell us where this point is without having to use your finger to point to this point. All right. And now with this one, for the 3D space, let's assume that this point, this green point, is located where x value is x, anything. All right. So the first coordinate for this point is going to be x. Now this point lies when at the location where y is equal to y. Right here, y. Right there, that's y. Right here, that's x. So the second one would be y, second coordinate. And the last coordinate, we look at the z value. So we have this z value right here, and that is z. Okay, so we have this last variable of z. So what we just did here is to use some sort of system to locate the point in the space, right? And once again, this is called coordinate system. And what you see here in this 3D space, down here you see this box, right? Made from the points that we use to locate this point P, all right? And by this same technique, when we go to 2D space, we have this rectangle made from 2 and 3. And that's why we call this coordinate system that we just used right here, rectangular coordinate system, right here. Coordinate system can be different. Sometimes it depends on what kind of values you use to locate the points. In this case, we use the shape of rectangles, boxes, so we call this rectangular coordinate system. And sometimes this is called Cartesian coordinate system. Well, when it comes to coordinate system, it doesn't have to be Cartesian. We have different way to locate the point. For example, if you look at this 2D space, instead of using a rectangle, you can use a circle like this. I'm gonna try my best to keep this a circle. Okay, let's assume that this is circle. All right, and then instead of using this 2 and 3, I'm going to put this radius of this circle right here. As you can see here, this circle is going to have a constant radius around it, right? So this is going to be r, radius. And then with this point and with this radius right here, it's going to create an angle between this radius and the x-axis, which means that here we are going to have theta. So right here we can use the circle shape to locate this point. So instead of using 3 and 2 from the x-axis and y-axis, we can locate this point by using the radius value. I don't know what it is here, but we can just put r. And then we can use the theta right here. And what we just did right here, it's called polar coordinate system, right? I'm sorry about this tight space. This is polar coordinate system. Down here, 3 and 2, this is rectangular. Or you can call it Cartesian. This is for 2D space. We usually have 2 coordinate system to locate a point. Now, when it comes to 3D space, it turns out that we have more coordinate systems. The first one that we just did here is this rectangular coordinate system. But then we can use the cylindrical coordinate system to locate a point too. Cylindrical. In this case, we are going to use an object with the shape of cylinder to locate a point. And then, not just cylinder, we can use a sphere to locate a point. And that is spherical coordinate system, number 3. Alright, but as of now, we are going to focus on just rectangular coordinates, or the Cartesian coordinates, to keep things simple. And once we master the computation on the rectangular coordinates or Cartesian, we can move to cylindrical or spherical later. Okay, so to summarize this slide, space is empty region. All right, and with empty region, we like to put a point. But once we have a point, we want to know the location of those points. To know the locations, we need something called coordinate systems. And we have different coordinate systems to apply, but the most popular one is Cartesian coordinate system, which you see right here. All right, and I need to tell you something about the XYZ axis in the 3D space. As you can see here on the figure on the right hand side, we have X right here, Y right here, and Z right here. Well, this is the most popular form of XYZ axis that you see. You see this a lot. But it doesn't have to be this all the time. The order can be moved around. I mean, the XYZ can be turned around. Okay? So it doesn't have to stay like this. But the order of XYZ has to follow the right-hand rule. So let's take a look here. Let's take a look. What if I want to put x-axis to be vertical like this? All right, x-axis vertical like this. Then after x, it has to be y, right? And if we follow the right-hand rule, we have to use the index finger for y, and that's when we get this y right here. Follow the right-hand rule. And after y, it has to be z. And by having the right-hand rule as the guideline, the next one would be z in the middle finger. Okay? Now, what if we want to start with z vertically, like this? I'm going to use green right here for z. After z, it's gonna repeat x again, right? So after z is gonna be x, so x has to go to the index finger, which is the next finger. So we have this x right here, and after x, it has to be y, and of course, after index finger, it has to be middle finger. And last one, we are gonna start with y vertically, right, like that. And after y is going to be z, and by right-hand rule, it's going to have to be index finger. After z, it repeats the x-axis, and by right-hand rule, it's going to go to middle finger right here. So, which means that you can have x, y, z at different order, but that order has to follow the right-hand rule. But most of the time, you are going to see this kind of order, right? Now, next slide. In this slide, we are going to talk about projection. That is the key word. So let's write down projection right here. Alright, that is the keyword. So when you think of projection, I want to associate this word with shadow and onto a plane. And next one, reduce dimension. By 1. Okay. Alright, so let's take a look at this point. P, and we know the location of this point by using the Cartesian coordinate system, this point P. And we know where it is by using x value, y value, and z value. Okay, now we want to project this point onto different planes. Okay, so what kind of planes are we talking here? The first plane is this one, x and y. Right, we are talking about this plane. So we want to project this point in 3D space onto this floor. So in order to do that, we are going to find the shadow of this point on the floor, right? So it's like shining a light from above. Let's assume that this is a light from above, and then we get a shadow down here. Okay, now this point is on xy plane. I want you to notice something. Xy plane, this means that on this plane, what value of z is going to be? Of course, at this point on this whole plane, z is going to be equal to 0. So when you see this word xy plane, you need to know that it's about z equal to 0. Alright, so what this means is that instead of having, well, I'm going to write it right here, sorry for the mess, x, y, z. Once this point is projected onto xy plane, we are going to have this, and that's why we have this point A. Point A right here, x, y, and 0. Okay, now when z is 0, it means that it's eliminated from the coordinate system. It means that the values that matter is just x and y. So in other words, instead of having a point in the space, it becomes a point on a plane. The dimension of this point, well, it's projected down to just 2D. All right. Point on 2D plane. So this is basically, we reduce the dimension of this point, the coordinate of this point, to just 2D. So, and that's why I wrote the reduced dimension by 1. Now let's take a look at a different projection, and this time we are going to work on XZ plane. So let's take a look at this XZ plane, where it is. So X right here and Z right here. Alright, so XZ plane, we are talking about this flat surface between Z and X axis. Alright, and when you see this plane, you know right away that on this plane, the Y value on this plane, this Y value is equal to 0. So just like point A, in case of point B, XZ plane means that Y equal to 0. And we are going to reduce the Y value here to 0. Project this point to XZ plane. So this goes down to be a shadow on XZ plane. And that's why we can see that Y value becomes 0, sort of like eliminated from the coordinates of this point. Okay, now let's take a look at the last one. It's the same concept. Now we want to find the projection of this point on YZ plane. So YZ plane right here. Now let's find that plane first. So Y right here and Z right here, and we are going to create this plane between the two axes, this whole plane. All right. Now we want to project this point onto this wall. So this is going to project in this direction onto the wall. All right. The shadow is going to show up right here. And by the way, when we talk about this red plane, YZ plane, we need to notice that on this plane, x equal to 0 on the whole plane. So YZ plane, x doesn't matter, basically x equal to 0. And the projection is going to come down in this direction, and we get this shadow. And of course, we get x equal to 0 right here. Like it's eliminated from the coordinate system. All right, so this is the kind of projection that you are going to see again in this class, but next time it might not be just a point, it might be shapes, right? But I think at this point you sort of know what it is to project something onto a plane, right? Find a shadow in different directions. Okay, now next let's take a look at the set for the variable. Okay, so in this case, if we work on 1D, we have only one variable, and the set that we are going to work on this variable is going to be a set of real numbers, and we use this R right here, real numbers. We are not going to deal with imaginary number at this point in this course, so everything is going to be real numbers. Set of real numbers. In 1D, we only have x, so that means x can be anything from -infinity to +infinity. Now, what if you work on 2 dimensions? When in 2 dimensions, you have x and y. And x and y can range from -infinity to infinity, and we call this set coordinate of x and y right here, this R2. So basically it's the same thing, set of real numbers, except that we have 2 dimensions, x and y. Now for 3 dimension, we have x, y, and z, and it's the same thing. They can be anywhere between -infinity and infinity, but in this case we have 3 coordinates. So we have 3 values of real numbers that can happen, that we can fit in. So what we are looking at here is the set of real numbers in 3 dimensions, and we use R3 as the notation for this set. Alright, so don't get confused when you see R3. Some of you might think that this is power of 3. No, 3 right here, 2 right here tells you about the dimensions of this set. Okay? Now, let's take a look at this example. We only have one information in this example, which is x equal to 3. And we are going to try to visualize this and find out about its geometry in different spaces. The first space that we are going to try to find out is in 1D. Then in 2D, R2, and then in 3D, R3. So with this same information, is it going to come out differently? Let's take a look here. So in 1D, we only have one variable to work with, which is x. So here we have this x-axis. Right, all the way here. And then we know that this point is, this is x equal to 3, and the location is right here, x equal to 3. So here we can see that with this information, we get a point in 1D. So we get one single point in 1D. What about in 2D? Let's find out. In 2D, we have 2 variables, and we have 2 axes. So right here, x-axis, and here y-axis. And the information that we have is x equal to 3, and of course it's right here when x equal to 3. But it turns out that right here x is also equal to 3, same here, here, all the way down here. So something is different in this case. X equal to 3 is not just one point, but multiple points. So when you work in 2D and you only have this one information of x equal to 3, it automatically means that y can be anything. So let's make a note here. Y can be anything in this case, right? Be anything. Because y hasn't been specified by the problem. So y can be anything as long as x is equal to 3. And that's why in this case, the same information, x equal to 3, becomes a straight line in 2D. Straight line in 2D. Now, what about in 3D? Let's start with the 3D space. X-axis, y-axis, and z-axis. And what we know right now is that x equal to 3. And y can be anything, right? Because it doesn't say anything about y, so y can be anything. And z, what about z? Z can be anything. So let's make a note here. In this case, y and z can be anything. And the reason for that is because it doesn't say anything about this two values, y and z. So let's I'm gonna change this value to this line to red. Okay, it's better. Now y can be anything, z can be anything, and it corresponds to all these points on this plane, right? On this plane, x is equal to 3 everywhere, but y and z can be different. So in this case, x equal to 3 becomes a plane in 3D. And if you compare this plane to the YZ plane, which can be constructed from the y and z axis like that, you can see that the plane that we had before at x equal to 3 is parallel to YZ plane. So you can make a note here that the plane we have here, this is parallel to YZ plane. Alright, YZ plane. So it's kind of interesting when one information can become different. A shape can have different shapes in different spaces, right? Now let's take a look at the next slide. This is about two terminologies, which are the quadrants and octants. They are a little bit different, but they have similarities. The similarities that these are the regions separated by the axis. Quadrants is something we use in 2D. 2D regions separated by the axis. So let's draw the axis. Alright, so we have x-axis right here and y-axis right there. Now, let's find out about the regions separated by these two lines. Of course, we get the first quadrant right here, Q1, and usually we specify the first quadrant when both variables are positive. So in this case, quadrant 1, x and y greater than 0, positive. Quadrant 2, move in counterclockwise direction, x less than 0 and y greater than 0. Quadrant 3, both x and y less than 0, all negative. And quadrant 4, x positive, but y is negative. So that's for 2D. We have quadrants, we have 4 regions. But in 3D, it's going to be a little bit different. With 3 axes separating regions, we are going to come out. We're going to have 8 regions to consider here. So in 3D, using 3 axes to separate regions, one right here, x, y right here, and z right here. Now usually we assign the first quadrant when all the variables are positive. The first octants usually correspond to the regions when all variables are positive. So let's take a look here. X positive go this way, y positive goes this way, and z positive goes this way. So when we use these red lines, we can see this box regions right here. It doesn't stop at the end of the box, but this box is gonna tell you the zone of this region. Octant 1 right here. In this octant 1, x, y, and z are positive. Alright, and you can move to octant 2. And in this octant 2, everything is about the same except that x becomes negative. You can see that in this octant 2 in the back, x is negative. Green here is negative. So here you can see that x negative, but y and z still positive. Okay, now let's move to octant 3. In this octant, you can see that x is already negative and y becomes negative too. So in octant 3, x and y negative and z still positive. And last one on the space above the xy plane. Right here, octant 4, here y is negative but x is positive. X positive, y negative, and z positive. So this is the last box on the top row. Alright, right here. Octant 4. And you can repeat this again when z is negative. Down here, z is negative, less than 0. And we get octant 5, octant 6, 7, and 8. Right? So, just regions in the space. Now, let's take a look at the intersection and curves. Right, first let's take a look at the curve. Usually when we talk about curve, you think of something like this. Curve, of course, when it comes to curve, usually it's not straight. You're supposed to be curvy. So what you see right here, this is a one-dimensional curve. Let me change that, doesn't look good. Okay, one-dimensional curve, let's say that it looks like that. Okay, this is 1D curve. Okay, now what about we try to flatten this curve to make it straight? I'm gonna make this curve go through something and it becomes a straight line like that. Usually when we go from red to blue right here, we call this line. Usually line is straight. Okay, so this line is 1D line and it's straight. Now, what about we increase one dimension more than what we have right here? Instead of 1D, we are going to try to make this curve becomes 2D curve. All right, I'm going to change this to 2D. So what's going to happen? It means that the dimension of this curve is going to increase by 1. So instead of just 1 dimension, it's going to become something like that. So what does it look like, 2D curve? It's a surface. So you can call 2D curves as surface. Alright, so when you talk about surface, you usually assume that it can be curvy, it can be anything, right? Has the freedom when it comes to shape. But what if we flatten the surface, what is it going to be? It's going to become straight, like that. Alright, a surface again, but a straight surface, and we usually call this straight surface, flat surface, as plane. So that is the first point I want to make. A plane right here is a surface when it's flat. So that corresponds to the first bullet here. Plane is a flat surface. Right. Well, plane can also mean a vehicle that can fly, but in this case, it's a flat surface, like a flat piece of paper lying on a table. Okay, now at this point, you know what a plane is, so let's find out what happens when we intersect two planes together. So we want to know what happens when we intersect two planes together. So let's take a look at the illustration down here. The first one, we are going to consider this green plane. Alright, this green plane. And this plane corresponds to x equal to 2. Alright, this plane, alright, I need to find out. Okay, this is the information for this plane, x equal to 2. Right, and then we are going to consider another plane. Let's take the blue one here. Right here, this blue one. Alright, and this blue one can be represented by this plane z equal to 5. As you can see here, on this plane z equal to 5, and y, x and y can be anything. So as you can see here, when we have two planes like this intersect each other, we have to find out about the points that are shared on both planes. And you can see when two planes intersect, we get this straight line between them. They are the points that are shared on both planes along this straight line. Okay, so what happens when two planes intersect each other? It means that you get a straight line. So you can put it right here, straight line. You might make a note here that you need to assume that both planes are not parallel to each other to get a straight line. If they are parallel, then it's going to overlap in a big region. So in this case, the first one, if the planes are not parallel, you get a straight line. Alright, let's go to the next one. We want to know what happens when three planes intersect one another. We are talking about three planes intersection. So we are going to work on this step by step. What about we intersect two planes and then we use the result to intersect another plane? From number 2, we know that two planes intersect, we get a straight line, right? So in the end, for this one, it's going to be the same as intersection of straight line, which is the result of the intersection of two planes and a plane, a line and a plane. So let's take a look here. We already have the lines right here, the red line, and then we are going to consider another plane, which is the orange one. I'm going to use black, right? So this orange, the third plane. Okay, now we consider this plane and we are going to intersect this plane with the line. And as you can see here, this plane with the red line, this red line, it's going to intersect at one point, which is right there. Okay, so two planes intersect, you get straight line. But if you have three planes intersect each other, you get a point. And once again, we assume that these planes are not parallel to each other. So here we have a point. As you can see here, each time you have an intersection, the dimension goes down by 1, right? Planes intersect becomes straight line, and intersect again becomes a point. Straight line, 1D, point 0, no dimension. Okay, now what if we don't have a plane when it comes to intersection? What if we have curved surface instead? Curved surface intersection. Then the result is not going to be a straight line, it's going to be a curvy line or a curve. Alright? So it's the same kind of thinking. Instead of straight, it becomes a curve.